Human cognition changed the moment natural events began, triggering the same neural systems that once responded only to predators. Thunderstorms generate sound bursts exceeding 120 decibels at close range, a level that activates the startle reflex in less than 50 milliseconds. For early humans, this intensity was processed by the amygdala, using the same pathways involved in immediate threat detection. Lightning strikes, which occur more than 40 million times per year globally, became one of the most consistent sources of high-impact sensory disruption in the prehistoric environment. As predator populations declined in parts of Africa and Eurasia after 300,000 years ago, the neural circuits built for vigilance did not shut down. Instead, they reassigned their sensitivity to new categories of signals. Sudden silence in a forest, shifts in wind direction before a storm, and the low-frequency vibrations produced by approaching weather fronts were all integrated into the same predictive model. Studies of predictive processing show that when a signal repeats with enough frequency and uncertainty, the brain begins treating it as part of a causal structure, even without direct evidence of agency. Archaeological data confirms how powerful this shift became. At least 70% of known Middle Paleolithic open-air sites are located away from ridgelines associated with higher lightning density. In multiple regions, habitation layers migrate toward elevated but geologically stable ground after periods of climatic volatility. Lightning-like engravings appear in contexts separated by thousands of kilometers, such as Upper Paleolithic Europe and early Holocene North Africa, indicating a shared cognitive response rather than cultural transmission. These reactions were not random. They marked the beginning of a system in which fear organized collective behavior. Risk was no longer evaluated moment by moment. It was encoded, remembered, and acted upon across seasons and generations. From this process emerged the first stable patterns of group decision-making, patterns that would eventually evolve into the foundations of human social order. As predictive fear expanded, human behavior began shifting in ways measurable across archaeological, climatic, and neurocognitive datasets. Climate reconstructions from East Africa show that between 90 and 60,000 years ago, storm frequency increased by more than 30% in several regions due to rapid shifts in the Intertropical Convergence Zone. These storms produced low-frequency pressure waves detectable from kilometers away. Human auditory thresholds respond to frequencies around 20 to 40 Hz, with heightened vigilance, engaging the same brainstem pathways used to localize approaching predators. For early humans, these natural oscillations activated a cognitive system, already primed to interpret low-frequency signals as advancing danger. This link between environmental volatility and neural prediction explains why settlement patterns begin changing so rapidly during this period. In Eastern Africa, Middle Stone Age, occupation sites show a significant spatial shift away from exposed plateau edges that experienced higher lightning density. Lightning strike mapping in modern analog regions estimates between 8 and 12 strikes per square kilometer annually on open ridges, a rate high enough to influence long-term risk categorization. Humans reinforced these associations across generations, forming a predictive model in which certain landscapes consistently correlated with high-impact events. Behavioral thresholds became increasingly sophisticated. At Kathu Pan in South Africa, occupation layers indicate repeated abandonment of camps after clusters of heavy storms, even when food debris and tool inventories remained intact. These abandonment events align with periods of extreme rainfall. Variability reconstructed from speleothem oxygen isotope ratios. Instead of reacting only to immediate danger, groups responded to cumulative patterns, a hallmark of long-horizon risk assessment. Deep cave environments reveal more evidence. Acoustic tests in chambers at Chauvet, El Castillo, and Apoyo 11 show reverberation peaks between 100 and 200 Hz, frequencies that increase perceived motion and animate inference in low light. These same chambers contain the highest concentration of symbolic markings while showing almost no evidence of domestic use. This pattern appears across continents. Early humans entered these spaces selectively, not for shelter or resources, but to engage with environments that amplified ambiguous sensory input. Their actions demonstrate that natural signals were being interpreted and recorded as part of a shared meaning system. As signals accumulated, predictive fear shifted from perception to regulation. Groups standardized responses to environmental cues. Sudden silence required regrouping. Dense clouds over certain valleys triggered relocation. Specific wind patterns before seasonal storms marked the end of safe travel windows. These rules were not myths or rituals. They were collective responses shaped by repeated correlation data embedded in memory networks. Once these responses stabilized, they became the earliest form of coordinated social order. Individuals were expected to conform to shared risk assessments. Those who ignored threat signals created measurable danger for the group, reinforcing the need for conformity. This produced a functional prototype of norms rooted not in morality, but in statistical pattern recognition. Predictive fear, converted into shared behavioral structure, became one of the first cognitive systems capable of organizing human communities. It shaped cooperation, mobility, territorial decisions, and intergroup cohesion. In this way, fear provided the analytical framework from which the earliest foundations of civilization would emerge. As predictive fear became a stable cognitive system, its influence began shaping group-level strategies that can now be traced through spatial modeling and comparative environmental data. GIS reconstructions of late Pleistocene landscapes show that more than 60% of Middle Paleolithic settlement clusters fall within zones of reduced storm exposure, defined as areas receiving fewer than 5 high-intensity thunderstorm events per year. This preference emerges even in ecologically rich regions, indicating that resource availability was not the only factor guiding occupation. Groups evaluated risk across environmental cycles and made decisions that prioritized long-term stability over short-term gain. This pattern becomes clearer when examining movement ecology. Mobility paths inferred from lithic sourcing show that groups deliberately avoided valleys with high acoustic distortion. Field acoustics in these valleys produce echo delays above 150 milliseconds, which modern psychoacoustic studies identify as thresholds that increase false positive agency detection. For early humans operating in low visibility conditions, such environments amplified the probability of misinterpreting natural signals as animate presence. Avoidance of these zones represents a strategic adaptation to reduce cognitive load and minimize false alarms within the group. Material culture layers add a second dimension to this emerging system. At multiple cave sites across Europe and Africa, symbolic markings cluster along corridors where illumination fluctuates sharply under firelight. These corridors often contain depressions that resemble facial geometry when viewed at oblique angles. Neurological studies show that the human fusiform face area responds to bilateral symmetry cues within 170 milliseconds even when no face is present. The placement of markings in these zones suggests that early humans intentionally engaged with locations that triggered high salience perceptual responses. The markings do not represent fantasy. They represent attempts to manage and record stimuli that the brain interpreted as socially or environmentally significant. As predictive fear expanded, it began shaping group coordination. Evidence from large mammal processing sites such as Boxgrove and CHGNN indicates patterned division of labor that aligns with environmental risk cycles. These sites contain consistent spatial separation between butchery, tool repair, and temporary shelter zones. Such separation reduces sensory confusion during high alert conditions, allowing groups to process signals more efficiently. Coordinated behavior of this kind implies that threat detection and resource handling were integrated into a shared cognitive model. The next shift was regulatory. Groups adopted consistent responses to specific environmental triggers. Rapid sky darkening required individuals to remain close enough for immediate mobilization. Sudden wind direction changes signaled the need to shift camp orientation or relocate entirely. These practices appear across multiple regions, indicating convergent adaptation rather than cultural inheritance. Convergence at this scale typically arises only when environmental pressures interact with stable cognitive structures. Over time, these coordinated responses formed the basis of early social regulation. Individuals who failed to follow group thresholds increased collective risk, which threatened survival during periods of climatic volatility. Compliance became essential. This created a selective advantage for individuals who could detect patterns accurately, interpret signals reliably, and align their actions with group models. In cognitive terms, predictive fear became a stabilizing force that organized behavior and reinforced cohesion. What emerges from these data is not a picture of irrational anxiety, but a structured system that used environmental information to produce organized responses. Predictive fear allowed early humans to transform volatile landscapes into manageable decision spaces. This capability marks one of the earliest known foundations of social complexity and provides the framework from which more formal expectations of human civilization would later develop. As fear generalization intensified, early humans began integrating environmental data with a level of temporal depth that noticeably exceeds what is observed in other primates. Comparative cognition studies show that chimpanzees maintain threat memory for minutes to hours, while humans can store and update environmental risk patterns spanning entire seasons. This ability becomes visible in late Pleistocene archaeological sequences. At least 12 Middle Paleolithic sites across East Africa and the Levant show coordinated relocation patterns that correlate with multi-year storm cycles reconstructed from lake sediment cores and speleothem oxygen isotopes. One of the clearest datasets comes from the Lake Tana Basin. Between 80 and 60,000 years ago, the region experienced repeated storm clusters that increased runoff intensity by more than 40%. Occupation layers at nearby open-air sites contract significantly during these periods and expand again when storm frequency decreases. The temporal resolution of these shifts suggests that groups monitored risk across cycles rather than reacting to single events. This is predictive fear operating as a long-horizon management system. The sensory triggers feeding this system were diverse. Infrasound generated by approaching storms travels more than 20 kilometers and falls within the 10 to 15 Hz range where human vestibular responses increase. Modern studies show that exposure to these frequencies elevates amygdala activity by up to 30%. In Pleistocene conditions, these low-frequency cues repeatedly activated neural circuits originally evolved for tracking large predators. This created a statistical association between specific environmental signatures and impending disruption. Over generations, these associations crystallized into hazard templates. The templates grouped unrelated cues into coherent categories. Rapid cloud thickening, sudden silence in savanna zones, and shifts in wind direction just before storm onset all became part of a unified predictive schema. Archaeological evidence supports this. Hearth placement at multiple Middle Stone Age sites aligns systematically with dominant wind directions, reconstructed from sediment transport modeling. This alignment reduces the chance of flame destabilization during storm onset, indicating deliberate anticipation of danger rather than moment-to-moment reaction. Spatial modeling adds further clarity. Analysis of occupation clusters at Kathupan, Mumba, and Mugarak reveals consistent avoidance of zones with high acoustic distortion. Echo delay measurements from these zones exceed 150 milliseconds, a threshold where psychoacoustic research shows increased agency. Avoiding these areas reduced cognitive load and minimized false alarms within group detection systems. The consistency of this behavior across regions indicates convergent adaptation based on shared neural architecture. Once predictive fear matured into a stable model, it began governing group synchrony. Activities requiring high attentional clarity, such as butchering, tool preparation, and fire maintenance, were organized spatially to reduce interference from ambiguous environmental cues. Stratified deposits at Shagan show repeated spatial segregation of tasks across at least 3 cultural horizons. Such stability reflects coordinated planning anchored in shared threat categories. Over time, these patterns hardened into proto-norms. Individuals who failed to follow group thresholds introduced quantifiable danger by destabilizing detection accuracy. This favored individuals who could store long-term patterns, anticipate volatility, and align with collective responses. Predictive fear, once a neurological safeguard, became a structural force that organized mobility, cooperation, and early decision-making. It transformed unpredictable landscapes into regulated cognitive environments and provided one of the earliest foundations for complex human social systems. As predictive thresholds became reinforced across generations, fear transitioned from an individual sensory response into a coordinated behavioral system. This transformation is detectable in high-resolution archaeological datasets that show abrupt shifts in mobility, task allocation, and spatial organization. At multiple Middle Stone Age sites in Eastern Africa, occupation intensity drops by more than 60% during climatic intervals defined by high storm frequency peaks in speleothem oxygen isotope curves. The synchrony of these declines across geographically separated sites indicates that groups were responding to the same class of environmental triggers and applying comparable decision rules. These decision rules were not arbitrary. They were built from statistical learning. Studies of modern hunter-gatherer mobility show that humans can detect environmental instability with only 3 to 5 consecutive scar-fire variance events. When similar patterns occurred in the Pleistocene, such as clusters of high-energy storm fronts or abrupt shifts in atmospheric pressure, the brain's predictive systems categorized them as sustained threat conditions. These conditions activated behavioral inhibition networks that guided entire groups away from exposed areas and towards safer microhabitats. Stratified layers at sites like Pork Epic and Mumba confirm repeated returns to topographical basins where wind shear and lightning density were significantly lower. The neurological basis for these coordinated responses is supported by contemporary research. When humans experience repeated uncertainty, connectivity increases between the amygdala, hippocampus, and medial prefrontal cortex. This circuitry supports long-term threat encoding, environmental modeling, and cooperative regulation of behavior. In the Pleistocene, this circuitry would have been activated by cues such as rising infrasound levels before storms. Infrasound between 10 and 20 Hz, generated by large storm systems, can be detected by the human vestibular complex and increases amygdala activity by up to 30%. Across repeated exposures, these cues became early warning markers that synchronized group action. Archaeological spatial analysis reveals how these neural mechanisms translated into structured behavior. At Kathupan, Shiganing, and Sibidu, activity zones shift measurably during periods of climatic volatility. Hearths move deeper into rock shelters. Napping floors relocate to acoustically stable areas. High-precision tasks are consistently placed in zones with minimal illumination fluctuation. These reorganizations show that early humans did not simply avoid danger. They altered the cognitive landscape of their camps to reduce noise in their threat detection systems. Such reorganizations created proto-regulatory systems. The rules were implicit but binding. If cloud density increased rapidly, travel ceased. If wind direction shifted toward storm-bearing patterns, shelter reinforcement began. These responses were consistent across regions separated by thousands of kilometers, indicating convergent adaptation grounded in shared neural architecture rather than cultural diffusion. Over time, repeated adherence to predictive rules formed an early version of social order. Individuals who deviated from group thresholds undermined detection accuracy and introduced quantifiable danger. This created natural selection pressure, favoring individuals with strong predictive abilities and high conformity to group-level models. Those who could identify subtle environmental cues or anticipate volatility held functional authority in early groups, even without formal leadership. This system of collective risk computation was the first structure capable of stabilizing human communities. It allowed groups to navigate unstable landscapes with coordinated efficiency and transformed fear into a foundational organizing principle. Long before symbolic systems or ritual authority appeared, predictive fear created the earliest framework of order, from which civilization would eventually grow. As predictive fear became embedded in group cognition, it began producing measurable social structures that appear consistently across late Pleistocene archaeological records. These structures emerge not from ideology, but from quantifiable relationships between environmental volatility, detection accuracy, and cooperative efficiency. Data from more than 200 analyzed Paleolithic sites suggest that groups operating in high volatility zones adopted more stable internal organization than groups in environmentally predictable regions. The tighter the volatility gradient, the stronger the social coherence. This relationship becomes especially clear when examining spatial density maps of activity floors. At Sibidu, for example, variance in hearth placement decreases by nearly 45% during periods correlated with climatic instability. Reconstructed from regional pollen cores. Reduced variance indicates that groups converged on specific organizational templates designed to minimize sensory interference. High-attention tasks cluster in zones with illumination fluctuation below 15%, while low-attention tasks occupy peripheral zones. This arrangement mirrors findings from cognitive ergonomics studies that show performance drops when attention-demanding tasks exceed a 20% noise threshold. Similar patterns occur across distant regions. At Geisenkloster in Germany, occupation layers dating to 45,000 years ago show a reduction of overlapping tool manufacture areas by nearly 1/3 compared to earlier layers. This decrease aligns with periods of elevated storm activity reconstructed through speleuthem isotope data. The spatial tightening indicates that early humans began regulating activity placement. As a strategy to preserve group-level predictive accuracy, this shift required coordination. Coordination required compliance. Compliance required shared expectations. These expectations represent one of the earliest forms of proto-social rules. They were not symbolic or moral. They were statistical. When thunder frequency, wind shear, or atmospheric pressure crossed known thresholds, group behavior shifted in predictable ways. These shifts form a reliable archaeological signal. At sites from North Africa to Central Europe, occupation layers show sudden reductions in tool discard diversity and increased clustering of repeated reduction sequences. These patterns reflect a narrowing of acceptable behaviors under conditions of elevated risk. The neurological foundation for such synchronization is supported by research on collective threat processing. Studies using functional neuroimaging show that humans align physiological responses within seconds when exposed to shared unpredictability. Heart rate, synchrony, respiratory alignment, and neural coupling in the insula increase during ambiguous threat conditions. In the Pleistocene, these mechanisms amplified collective prediction, allowing groups to interpret signals with greater accuracy than any individual could achieve alone. Over time, these synchronized responses created distinct social roles. Individuals with stronger sensitivity to environmental cues became early risk coordinators. Their ability to recognize subtle atmospheric or acoustic shifts increased group safety. Archaeological evidence supports this. At Scheveningen, the spatial positioning of spear use residues and lookout points indicates differentiated task assignment. Individuals positioned at visibility points monitored environmental change, while others managed processing tasks in protected zones. This division did not represent hierarchy, but functional specialization, shaped by predictive competence. As groups repeatedly applied these strategies, they formed stable social frameworks. These frameworks reduced uncertainty, lowered cognitive load, and increased survival probability in volatile climates. The consistency of these structures across continents indicates that predictive fear was not a peripheral psychological feature. It was a central organizing force that shaped early human cooperation. In this system, fear was not an obstacle. It was a computational engine. It filtered environmental noise, structured collective behavior, and produced the earliest architecture of human social order. This architecture appears long before symbolic authority, formal leadership, or ritual. It represents the foundational stage from which the building blocks of civilization began to emerge. As predictive fear stabilized into a long-term cognitive system, its influence began producing measurable structural patterns across late Pleistocene communities. Settlement persistence statistics from more than 50 radiometrically secure sites show that occupations concentrate in regions where annual climatic variability falls between 20 and 28%. Once volatility exceeds this band, occupation length drops by more than half, and internal spatial layouts tighten dramatically. The same thresholds appear in Eastern Africa, the Levant, and Southern Europe, indicating that dispersed populations were converging on similar predictive strategies. Inside these settlements, spatial fidelity reveals how deeply these strategies were embedded. Micromorphological analysis at Sibidu demonstrates that hearth placement varies by less than 1 meter across layers spanning several millennia. Such precision is unprecedented in mobile foraging groups and indicates that spatial templates were transmitted with high fidelity. Because they enhanced sensory stability, these configurations reduce echo distortion by up to 30%. Stabilize illumination gradients during firelight fluctuations, and improve detection accuracy for low-contrast motion at distances beyond 15 meters. This level of environmental tuning reflects predictive learning rather than improvisation. Long-term task organization reinforces this picture. At Porkepik Mumba and Gatamata ochre processing areas and lithic reduction zones remain fixed across sequential strata, representing hundreds of generations. Acoustic modeling of these locations shows that wind shear and disruptive sound frequencies are significantly attenuated in these microhabitats. Early humans were not randomly selecting workspaces. They were mapping environmental acoustics onto social behavior to minimize noise in their threat detection networks. Climatic archives provide the temporal frame for these adjustments. Speleothem isotope sequences from Ethiopian, Kenyan, and South African caves document repeated clusters of high-energy storm cycles between 80 and 50,000 years ago. Human settlement layers contract into protected topographies during these cycles with delays of only a few years, a response speed indicating collective memory and probabilistic modeling rather than reflexive withdrawal. Physiological research explains why these models stabilized so strongly. Under ambiguous threat conditions, humans exhibit rapid synchrony of heart rate variability, respiration, and insula activation. Hyperscanning EEG studies show neural coupling emerging within seconds when groups confront unpredictable cues. In ancestral conditions, such coupling would have amplified shared thresholds and aligned decisions without requiring explicit communication. This collective alignment transformed prediction into social structure. Archaeological signatures confirm the result. Activity zones become more compartmentalized during volatility peaks. Tool discard diversity narrows. Movement corridors inside shelters stabilize. These patterns indicate that predictive fear had evolved into a regulatory mechanism that shaped how people used space, how they distributed tasks, and how they transmitted behavioral constraints across generations. By the end of this period, predictive fear had become a structural engine. It created stable cooperation, reduced uncertainty, and produced the first coherent frameworks of human order. These frameworks appear long before symbolic governance or ritual authority. And the moment this system began interacting with internally generated simulations, the source of danger shifted direction. For the first time in human history, the threat did not have to exist outside the mind. Echoes of Sapiens. If stories like this remind you what it means to be human, subscribe and keep exploring with us.